Okay, good.
Yes,
So,
sir.
okay, so section 4.4. So, the fundamental counting principle. For each sequence of two events in which the first event can occur in m ways and the second event can occur in n ways, the events together can occur in a total of m times n ways. So you just multiply them together. So first, if the number of events is very small, we can look at their outcomes by looking at a tree diagram. So suppose a tourist can travel from Germany to France by car, by plane, by car, and by train, or by train, and can travel from France to England by car, by boat, or by plane. Car, boat, or plane. Car, boat, or plane. List all possible ways she can travel from Germany to England using this tree diagram. So let's do that. So let's make it smaller. A little bit smaller. Okay, there. Now you can see it. So from Germany to France, they can go by plane, boat, train. From France to England, car, boat, and plane. So they can go plane, then car, plane, boat, plane, plane, car, boat, car, plane, train, car, train, boat, train, plane. So these 9 different ways are how they can go from Germany to England. Okay. Good. So factorial. So let's define factorial recursively as, so this little exclamation point is the factorial notation. So 0 factorial is defined as 1. N factorial, it is defined as n times n minus 1 factorial. So for example, 3 factorial is 3, actually, times 2 factorial. Oh, there it is. And 2 factorial is 2 times 1 factorial. And 1 factorial is 1 times 0 factorial. But 0 factorial is 1. So 3 factorial is 3 times 2 factorial. 2 factorial is 2 times 1 factorial. Just keep going on this recursive definition. 1 factorial is 1 times 0 factorial, but then you end because 0 factorial is 1. Therefore, 3 factorial is 3 times 2 times 1. I don't need to add the extra 1 there. So 6. 5 factorial is, well, doing the same thing we did here. It's 5 times 4 times 3 times 2 times 1, 120. So let's see if I can, hopefully this. Okay, so let's do this. Okay, so we want here, wait 1 second. Okay. Okay, so we want 5 factorial. That's what we want. Okay. So let's do 5. Good. Go to math. Go to PRB. Go to PRB. There it is. Oh, I see. There it is. PRB. They have, oh, this is the CE. Okay, go to PRB. And the 4th one down is factorial. And so 120. Let's go to what, Excel? No, let's just do that one. Okay. Well, let's see if this works. No, that doesn't. Okay.
I think there's one function on Excel is, yeah, that one, fact.
Yeah, it's factorial. Yeah, I know, but I was seeing if it would. I was just trying to see if it would do it. Okay, so factorial. So factorial 5. And let's see, Mathematica. Let's do Mathematica. So let's do factorial 5. But 5 factorial also works. Okay, so you can either do it with the little exclamation point or not. R. Ooh, I don't remember R. Let's. Oh well, this is. I'll try R for a second. I don't remember. Let's just try this. It's probably not going to work. Yeah, it's not going to work. Fact. I think it's factorial 5. Yeah, whatever. I can never remember. Oh, it's factorial. So in R, it's factorial. Okay. So permutation. A permutation of n different objects taken R at a time is an ordered arrangement of R objects out of the n objects. So in permutations, we're talking about an ordered arrangements. So suppose I have 10 books, and I tell you from these 10 books, pick your top 3 books that you want to read, and they must all be different. You can't choose the same book. So they must be, choose 3 different books from these 10 books to read. So how many different ways are they to do that? Well, for the first book, you can choose any one of the 10. For the second book, well, since you can't choose the same book, there are only 9 remaining. And for the third book, well, there's only 8 to choose. So it'd be 10 times 9 times 8. So the number of different permutations of n different distinct objects taken r at a time without repetition is NPR. N times n minus 1 times n minus 2 times dot, 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 n minus r plus 1. It's, what I said, 10p3. So you do 10 times 9 times 8, because you're choosing 3 books. So you start at the 10, and then you keep multiplying down till you've multiplied out 3 numbers. It is also n factorial over n minus r factorial. Suppose, well, I tell you that, I want you to choose of these 10 books, choose, 3 books. And I didn't say you can't choose the same one. So the first book, well, there's 10 of them you can choose. For the second one, well, I'm doing it with replacement. So I put the book back into the pile. So I'm going to do it with replacement here. And so now the choice is still 10 books. And for the third one, well, it's still 10 books. So 10 times 10 times 10. So if I'm allowed to do this with replacement, then it's just 10 cubed. So the number of different permutation of n different distinct objects taken r at a time with repetition is n to the r. So 10 cubed, so 10, so n to the r. The number of permutations of n different objects taken all at a time around a circle is n factorial. You just go around the circle. Now, if instead of having 2 things, you have, well, r differing things to choose, k differing to choose, then, well, the number of permutations of n objects taken all at a time with n1 objects are identical of one type, n2 objects are identical of the second type, dot, 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 nk objects are identical of a k type is n factorial, where n factorial, where n is n sub 1 plus n sub 2 plus n sub 3 plus dot, 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 n sub k. So it's n factorial over n1 factorial times n2 factorial times dot, 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 n sub k factorial.
Professor, so permutation can only be used with replacement?
No. There's without, there's with. 2 different formulas.
Okay.
You're saying this one, the NPR,
Yeah.
yes. The NPR, that symbol can only be used when you're doing without replacement. Yeah.
So with replacement, we have to use n factorial over n factorial 1.
No. With replacement,
Uh-huh.
then it's into the R.
N to the r. Oh, okay.
Without replacement, then it's the n factorial over n minus r factorial. It's the NPR. Okay.
Okay.
So if you keep taking them away and you don't put them back in. Okay, so let's do 10p3. Oh, I already said that as an example for some reason. So 10 times 9 times 8, 720. 15p4. So 15 times 14 times 13 times 12. And so 32,720. Okay, so where I did those. Combination. A combination of n different objects taken r at a time is a selection of r objects out of the n objects without regard to the order of the arrangement. So if you have an ordered list, you do permutations. If ordering does not make any difference, if there's no ordering, then you use combinations. The number of different combinations of n different objects taken at a time without repetition is NCR. It is the binomial coefficient, NCR. It is n factorial over r factorial n minus r factorial. It is the NPR over r factorial. The number of different combinations of n different objects taken at a time with repetition is n plus r minus 1 CR. It is n plus r minus 1 factorial over r factorial n minus 1 factorial. Let's look at Pascal's triangle. So Pascal's triangle is, well, we start out here at 1, drop down to 1, drop down to 1, and then add 1 plus 1 is 2, drop down to 1, 1 plus 2 is 3, 2 plus 1 is 3, drop down to 1, drop down to 1, 1 plus 3, 4, 3 plus 3, 6, 3 plus 1, 4, drop down to 1, drop down to 1, 1 plus 4, 5, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5, drop down to 1. Lastly, drop down to 1, 5, 1 plus 5, 6, 5 plus 10, 15, 10 plus 10, 20, 10 plus 5, 15, 5 plus 1, 6, drop down to 1. And you can keep going forever. But I just did this far. Let's recall the binomial theorem from your previous classes. X plus y to the n is equal to the sum r equaling 0 to n of NCR x to the n minus r y to the n. Now, in statistics class, since notice, well, that Pascal's triangle is symmetric, it turns out that it doesn't matter the order if you go, you know, descending powers of x or ascending powers of x. It doesn't really matter by symmetry. So in statistics, we actually write the binomial theorem in the other direction. So we write it as the sum r equaling 0 to n, NCR, x to the r, y to the n minus r. So the binomial coefficient, NCR, again, NCR in this binomial coefficient notation, n factorial over r factorial n minus r factorial. So to figure out 6C2, you would start with a 6, because there's a 6 here. Keep multiplying out till you've multiplied out two numbers. So 6 times 5 over 2 factorial. So 30 divided by 2 is 15. 8C3. Start at 8 times 7 times 6. You end there at 6 because you've written 3 numbers over 3 factorial. Well, the 6's cancel. 8 times 7 is 56. So the reason for this is the following. So 8C3 is 8 factorial over 3 factorial, 8 minus 3 factorial. So 8 factorial here over, well, 3 factorial times 8 minus 3, which is 5 factorial. Notice that the 5 factorials cancel. So all you have in the numerator is 8 times 7 times 6 over 3 times 2 times 1. And that always occurs. So that's why I gave you this sort of short cut here, where it's NPR over n factorial, over r factorial. Okay, so something like 15C4, 15 times 14 times 13 times 12, you only write out 4 numbers, over 4 factorial. The 12s cancel. 14 divided by 2 is 7 times 15, 105 times 13, 1365. A bag contains 7 red balls, 5 white balls. 4 balls are drawn at random. What is the probability that all of them are red? And so let's do this. B, 2 of them are red, 2 of them are white. So first off, let's figure out the denominator first. I have a total of 12 balls. Since they are balls and I'm selecting them, I don't care the order in which I select my balls, right? Who cares? So I'll just, do NCR because order doesn't make any difference when I'm selecting balls from a bag. And so combinations. So it's 12C. In this case, I want 4 balls. I'm choosing 4 balls. So 12, choose 4. Next, there are 7 red balls. I want to choose all of them to be red. So I want all 4 to be red. There are 5 white balls, and I want to choose none of them to be white. 7C4, 35, 5C0, 1, 12C4, 495. And so I get 7 over 99. Next, I want 2 of them red and 2 white. So, well, there's still 12 balls, and I'm choosing 4 of them. There are 7 red balls. I want to choose 2 of them to be red. There are 5 white balls, and I want to choose 2 of them to be white. So 7 choose 2 is 21. 5 choose 2 is 10. 12 choose 4 is 495. So 14 over 33. A bag contains 7 red balls, 4 blue balls, 5 white balls. 4 balls are chosen at random. What is the probability that one of them is red and 2 of them are white? So I want 1 red ball, 2 white balls. There are a total of, well, let's see, 7 red plus 4 white plus 7 red, 4 blue, and 5 white balls. That's 12, 16 balls. And I'm going to choose 4 of them. So 16, choose 4. Again, these are balls, so it's being chosen. So order doesn't make any difference. So I'll do combinations. Next, there are 7 red balls. I want to choose 1 red ball. There are 5 white balls. I want to choose 2 white balls. So I've chosen 1 red and 2 white balls. So I've chosen 3 balls, but I want to actually choose 4 balls. So the remaining 1 ball that I choose can neither be red nor white. So there are a total of 12 red, white balls. The remaining 4 balls are neither red nor white. And so I want to choose one of those non-red white balls. I want to choose my blue balls. And so there are 4 non-red, non-white balls, and I'm choosing one of them. So 7 choose 1, 7, 4 choose 1, 4, 5 choose 2, 10, 16 choose 4, 18, 20. And so I get 2 out of 13. Okay, so let me show some properties of Pascal's triangle. So first, that NC0 is 1. Meaning all these guys here, all these first elements, all the leftmost entries in Pascal's triangle for every row is equal to 1. So I want to show that. Oh, actually, I think when I did this, I think I did it better. So let me go here. I think I may have written out some additional comments here. Okay, so, oh, yes, okay, so good. So let's show that NC0 is equal to 1. So I'm just going to use the definition here of the factorial definition of NCR. And so I have here that NCR is n factorial over r factorial n minus r factorial. I'm going to replace r here by 0. And so I get NC0 is n factorial over, well, instead of r, 0 factorial over n minus, well, again, instead of r, I'll put 0, n minus 0 factorial. And so n minus 0, well, that's easy. That's just n. And sorry. Doing one thing and more than one thing at one time. N minus 0 is just n. 0 factorial, well, by the recursive definition of factorial, I have that 0 factorial is equal to 1. The n factorials cancel, and so I just get, well, 1, and that's what I wanted to show. Next, NCN is equal to 1. And so, let me actually, well, actually, let me move to the other one. So I'll probably have that one always to Pascal's triangle. Okay, so this means that, so NCN equaling 1 means that, well, the leftmost, that this end of Pascal's triangle is always equal to 1. Okay, so, and just note that actually, as it says, we could prove this using its property 4 below. Actually shows this, but we'll do it anyway. So again, we're going to use the fact that NCR is n factorial over r factorial n minus r factorial, and the fact that 0 factorial is 1, just like in the previous proof. So let's replace r here by n. So this is n factorial over, well, instead of r, it'll be n factorial times n minus, instead of r, it'll be n factorial. Well, n minus n is 0. 0 factorial is 1. The n factorials cancel. And so this is equal to 1. Next, property 3, NC1 is equal to n. And so let me show you that. So this just says that if I look at the second, if I'm going from left, reading from left to right here, this second entry here just counts the row. This is row 0, row 1, row 2, row 3, row 4, row 5, row 6. So this entry here just counts your rows. Now also note, well, of course we didn't show that. This is what we're showing, this one here. Okay, so let's do that. So I'll use the following facts to prove this. First, again, the definition of NCR in terms of factorial. So NCR is n factorial over r factorial times n minus r quantity factorial. And I'll use the fact that 1 factorial is equal to 1, and that n factorial is n times n minus 1 factorial, by, again, the recursive definition of factorial. Oh, this is good. Wait 1 second. In a car, and of course, it's a little crowded, so everything falls. Sorry about that. I'll change it up. Sorry. Okay, so I'm sorry. There. Okay, so sorry about that. We're doing this. Okay, so let's do NC1 is equal to, well, let's replace r here by 1. So it's n factorial over, instead of r, 1 factorial times n minus 1 factorial. 1 factorial is 1. I can write n factorial as n times n minus 1 factorial. Then the n minus 1 factorials cancel, and all that remains is n. And that's what I wanted to show. Oh, good grief. Okay, 1 second. Next, I have here, I want to show that NCR is equal to n times n minus r. I want to show that NCR is equal to n c n minus r. Okay, so let me show you this first. That's just symmetry. So this says that if I look at one side of Pascal's triangle, it's a mirror image of the other side. So these are mirror images of each other. And so this just says that Pascal's triangle is symmetric. Okay, so let's try to show this. Okay, so let's do that. So again, I will use the fact that NCR is n factorial over r factorial n minus r factorial. So let's look at NC n minus r. See what that comes out to be. So let's replace r by n minus r. So this is, so NC n minus r is n factorial over, instead of r, n minus r factorial times the quantity n minus r. And so there's a minus sign outside the parentheses. And so this changes from, this becomes n minus n plus r. The n's cancel, And so this is just r factorial. But n factorial over r factorial, n minus r factorial, is just NCR. And that's what you wanted to show. So next, NCR plus NC n minus r is equal to n plus 1 CR. And so let's show this. So what this says is that to figure out, let's say this number, you just add what's above it. 5 plus 10 is 15. 10 plus 10 is 20. And that's how I figured out Pascal's triangle.
Yeah.
So this is how I made Pascal's triangle. So that's, I want to show that property. So again, let's use the fact that NCR is equal to n factorial over r factorial, n minus r factorial. And that n plus 1 minus r factorial by the recursive definition of factorial is n plus 1 minus r times n minus r factorial. And again, using recursive definition, n plus 1 factorial is n plus 1 times n factorial. And again, by using the recursive definition of factorial, r factorial is r times r minus 1 factorial. So let's do this. So NCR, n factorial over r factorial, n minus r factorial, plus NC r minus 1, n factorial over r minus 1 factorial, times n minus r minus 1 factorial. Well, let's change all the signs inside the parentheses, since there's a minus sign outside the parentheses. So this becomes n minus r, minus and minus become a plus 1. And so let's write this as n plus 1 minus r factorial. Let's write r minus, let's find a common denominator. The common denominator is r factorial times n plus 1 minus r factorial. So let me multiply and divide this first term here by n plus 1 minus r. That will make this into an n, this n minus r factorial, into an n plus 1 minus r factorial. And let's multiply and divide the second term here by r. That will make the r minus 1 factorial into an r factorial. And so you'll get a common denominator. So now the numerator, well, for this one is r times n factorial. For this one, well, let's multiply the, let's write this as n plus 1 minus r. So let's consider as n plus 1 is one entity. So let's multiply n factorial times n minus n plus 1 factorial, which is n plus 1 factorial. And I have a minus r times n factorial, which will cancel. So I just have n plus 1 factorial in the numerator. And I have an r factorial in the denominator, and n plus 1 minus r factorial in the denominator. Which means, well, if I replace r here, n here by n plus 1, that's just n plus 1 CR. And that's what I wanted to show. Okay, so next, the binomial theorem. So next, let's show the binomial theorem. We will show the binomial theorem using the notation in statistics. So in mathematics, as I said, we usually write it n plus x plus y to the n equaling k equaling 0 to infinity of the binomial coefficient n choose k, x to the n minus k, y to the k. We're going to instead use the notation from statistics. So in statistics, it's the same theorem, it's just written slightly differently. So p plus q to the n equals the sum, r equaling 0 to n of NCR P to the R Q to the N minus R. So let's try to prove this using mathematical induction. So first, let N equal 0. And so the sum R equaling 0 to 0 of 0 CR X to the, I would say P to the R Q to the 0 minus R. Well, R goes from 0 to 0, so R is 0. So 0 C0, P to the 0, Q to the 0. 0 C0, well, from property 1, we know that's 1. So from the very first property we proved, this first term is 1. Assuming, let's assume that P and Q are not 0, in which case P to the 0 is 1 and Q to the 0 is 1. Otherwise, just assume that P to the 0 is 1 and Q to the 0 is 1, in which case we get 1. So therefore, P plus Q to the 0 is 1. And so I've shown that these are equal when N is equal to 1. Let's do the induction case. Suppose that P plus Q to the N, capital N, let's see if I can actually say that. So P plus Q to the capital N is equal to the sum R equaling 0 to capital N C R, P to the R, Q to the capital N minus R. So I want to show that this formula works when I replace capital N by capital N plus 1. So let's look at P plus Q to the capital N plus 1. By the properties of exponents, this is the same as P plus Q times P plus Q to the capital N. But P plus Q to the capital N, well, we said that it's equal to this sum here. And so this is equal to P plus Q times the sum R equaling 0 to capital N CR, P to the R, Q to the capital N minus R. Let's multiply P inside the parentheses. And so it's going to be the same, except I'm going to add 1 here to the exponent of P. So this is equal to the sum R equaling 0 to capital N CR, P to the R plus 1, because I multiply by one additional power of P, Q to the power capital N minus R. Plus, now let's multiply everything here by Q. So using the distributive property, plus, and so I'll just add one additional X power Q. So the sum R equaling 0 to capital N CR, P to the R times Q to the capital N minus R plus 1. Again, because I multiplied by one additional power of Q. So now, let me, wait 1 second. Let me get rid of that. Okay. Next, let me write out the nth number here and the 0th term here. So let me write out, so let me just rewrite these here, but I'm going to write out specifically the 0th term here. So when R, let's replace R equaling 0 here. So this is N, capital N C0, P to the 0, Q to the N minus 0 plus 1. And R here doesn't go from 0 to N, but since we wrote out the 0 term, it goes from 1 to capital N. So the sum R equaling 1 to capital N of capital N CR, P to the R, Q to the capital N minus R plus 1. Now let's write out the last term here, the nth term. And so let's replace R here by capital N. So it's capital N, C capital N, times P to the capital N plus 1, plus, times Q to the capital N minus N, plus this term, but without the last capital N term. So the sum R equaling 0 to capital N minus 1, capital N CR, P to the R plus 1, Q to the capital N minus R. So NC capital N is 1 by property 2. N minus capital N minus capital N is 0. Q to the 0 is 1. Therefore, I'm multiplying all the P to the capital N plus 1 by a whole bunch of 1s. So this first term is P to the capital N plus 1. Let's just rewrite the second and third term. I'm not going to do anything here. I don't think I'm doing anything. No, I'm just rewriting them. So I'm not doing anything here. Next, NC0, capital NC0, by the very first property that we proved is 1. P to the 0 is 1. Q, N minus 0 plus 1 is just capital N plus 1. And so this last term is just Q to the capital N plus 1. So now, rewrite this first term, P to capital N plus 1. This last term, Q to the capital N plus 1. Rewrite this third term here, R equaling 1 to capital N C R, P to the R, Q to the capital N minus R plus 1. Now, for this term here, let K equal R plus 1. And so when R is 0, K is 1. When R is capital N plus 1, K is capital N. Capital N C R, but R is, well, K minus 1. P to the R plus 1, but R plus 1 is K. Q to the capital N minus R, but again, R is K minus 1. So now, let's rewrite the first term. So the first term remains the same. This is P to the capital N plus 1. The last term remains the same, Q to the capital N plus 1. This third term here remains the same. The sum R equaling 1 to capital N CR, P to the R, Q to the capital N. Oh, but I wrote this is Q to the capital N plus 1. I can write the plus 1 after it, and then minus R. So I just rewrote I just changed the order of N minus R plus 1, wrote it as N plus 1 minus R. Now, I don't like K's, so I'll replace K as R. So I just write this. Instead of K's, I'll put R's here. So the sum R equaling 1 to capital N C R minus 1, P to the R, Q to the capital N. Oh, again, this is a capital N minus and minus become a plus 1. So capital N plus 1 minus, instead of K, I'll call it R minus R. But now I rewrite the first term and the last term, P to the capital N plus 1, Q to the capital N plus 1. Notice the sum here goes from R equaling 1 to capital N, sum K, R equaling 1 to capital N. This is a P to the R. This is P to the R. This is Q to the capital N plus 1 minus R. So I'll factor those out. And then this first term is capital NC. Oh, I write it here. Capital NCR. And then this term is capital NCR minus 1. But by the previous, by the previous, by this property number 5, by property number 5, there it is right here. So by property number 5 here, in capital NCR plus capital NCR minus 1, it's capital N plus 1 CR. So let's just replace that. Let's rewrite the middle term here. The sum, let's rewrite the sum. This is the sum R equaling 1 to capital N plus 1, CR, P to the R, q to the n plus 1 minus r. Now, let's rewrite p to the power capital N plus 1 as, well, q to the 0, which is 1. So n plus 1 minus n plus capital N plus 1 minus capital N plus 1 is q to the 0. So I'll just write that there. I've just multiplied by 1, haven't done anything. Similarly, capital N plus 1 c capital N plus 1 is just 1. So I haven't changed anything here. And lastly, let's rewrite this last term here. Q to the capital N plus 1. Well, p to the 0 is 1. So if I multiply by 1, I haven't changed anything. N capital N plus 1 C0 is also 1. So multiplying by that doesn't change anything. And so next, let's write this last term as my first term. Capital N plus 1 C0, p to the 0, q to the capital N plus 1 minus 0. So I haven't changed anything. I just subtracted 0 here. Plus, we write the same the sum term here. The sum r equaling 1 to capital N plus 1 CR, p to the r, q to the capital N plus 1 minus r. And let's write this first term here as my last term. Capital N plus 1 C capital N plus 1 times p to the capital N plus 1 times q to the power N plus 1 minus capital N plus 1 minus capital N plus 1. But this is just, each of these are just terms in this series. So this is just the sum, r equaling 0 to capital N plus 1, capital N plus 1 CR, p to the r, q to the capital N plus 1 minus r. So when r is 0, that's this first term. When r is capital N plus 1, it's this last term. So, but this is just the same as this, where we replace n here, capital N here, by capital N plus 1. Therefore, the induction case holds. Therefore, by the principle of mathematical induction, p plus q to the n is equal to the sum r equaling 0 to n, NCR, p to the r, q to the n minus r. And this is true for every whole number n. Next, absorption. So let me show absorption. That r times NCR is equal to n times n minus 1c r minus 1. And so I'll just use the fact that NCR is equal to n factorial over r factorial times n minus r factorial. And that by the recursive definition of factorial, n factorial is n times n minus 1 factorial. And we'll use this algebraic fact that differences are translation invariant. N minus 1 minus r minus 1. Let's change all the signs inside the parentheses. Is n minus 1 minus r plus 1. So the ones cancel. So n minus r. So I can rewrite n minus r as n minus 1 minus r minus 1. So let's show this. So r times NCR is, well, NCR is n factorial over r factorial, n minus r factorial. I'll write n factorial as n times n minus 1 factorial. I'll write, oh, I should have said that. I'll write r factorial as r times r minus 1 factorial. The r's cancel. Let me write the n out in front. So what remains is n minus 1 factorial over r minus 1 factorial times n minus r, but I'll write n minus r as n minus 1 minus r minus 1 factorial. But then this using this definition of NCR is n minus 1 CR minus 1. And that's what I wanted to show. Let me show this next absorption property, that R times R minus 1 times NCR is equal to N times N minus 1 times N minus 2 CR minus 2. So again, as always, we use the factorial definition of NCR. So NCR is n factorial over R factorial n minus R factorial. We'll use the recursive definition of factorial to write n factorial as n times n minus 1 factorial. But n minus 1 factorial is n times n minus 2 factorial. So I'll rewrite n factorial as n times n minus 1 times n minus 2 factorial. We'll also use, and also this is R factorial is R times R minus 1 times R minus 2 factorial. We'll also use the fact that, well, differences are translation variant, that n minus 2 minus R minus 2, the 2's cancel, is n minus R. So let's try to show this. So R times R minus 1 times NCR is equal to, well, NCR is n factorial over R factorial n minus R factorial. Let's write n factorial as n times n minus 1 times n minus 2 factorial. Let's write R factorial as R times R minus 1 times R minus 2 factorial. The R and the R minus 1s cancel. So you just have an R minus 2 factorial in the denominator. Let's write the n and the n minus 1 on front of the this fraction. So I just have an n minus 2 factorial in the numerator. Let's rewrite n minus R as n minus 2 minus R minus 2. But then if I look at this NCR definition, and I replace n by n minus 1 and R by R minus 2, this fraction here is just n minus 2 CR minus 2. And that's what you wanted to show. Next. And so that was, again, one of the absorption properties. Let me prove the following absorption property, which is really, well, that RPK times NCR is equal to NPK times N minus K CR minus K. So it turns out that, oh, I didn't say that, that if you let K equal 1, that this is property 7. If you let K equal 2, this is property number 8. So property 7 and 8 are just subcases or special cases of property 9. The reason for writing out property 7 and 8 explicitly is because we're going to be using these explicitly. So it's nice to actually have them written down. So you can just look at them, say, oh yes, that's the property that we're using. Okay, so we're just going to use the factorial definition of NCR and PCR, NPR, PCR, NPR. And so NCR is n factorial over R factorial n minus R factorial, and NPK is n factorial over n minus K factorial. So let's do that. So NPK is n factorial over n minus K factorial. N minus K CR minus K is n minus K factorial over R minus K factorial times n minus K minus R minus K factorial. Now, of course, the n minus K factorials cancel. N minus K minus R minus K, the K minus K's cancel. So this is just n minus R factorial. Let me write my denominator. as, well, n minus k factorial, n minus r factorial, and my numerator is n factorial here. And then let's multiply and divide by r factorial. But now this, by the factorial definition of permutations, is just RPK. And this, by the factorial definition of combinations, is NCR. And that's what you wanted to show. Next, let's show here that the sum I equaling 0 to k of ACI times BCK minus I is equal to A plus B CK. So, x plus 1 to the A is, by the binomial theorem, the sum I equaling 0 to A of ACI x to the I 1 to the I minus A minus I. 1 to any power is just 1. So this is the sum I equaling 0 to A of ACI x to the I. Let's look at x plus 1 to the B. Again, by the binomial theorem. This is just the sum j equaling 0 to B, BCJ, x to the j, 1 to the B minus j. But 1 to any power is just 1. So this is just the sum j equaling 0 to B, BCJ, x to the j. Let's distribute these, multiply these together. So this is just equal to the sum I equaling 0 to A, the sum j equaling 0 to B, ACI x to the I times BCJ x to the j. So this is equal to the sum I equaling 0 to A, the sum j equaling 0 to B of, well, ACI times BCJ times x to the I times x to the j. Well, by the properties of exponents, this is just x to the power I plus j. Let k equal I plus j. So this exponent I plus j becomes just x to the k. Since k is equal to I plus j, then j is equal to k minus I. So this is BCJ becomes BCK minus I. ACI is just ACI. So this becomes, well, the sum I equaling 0 to A of the sum k equaling, well, when j is 0, k is I, to when j is B, k is equal to A plus B. So this is the same as the sum k equaling 0 to A plus B, the sum I equaling 0 to k of ACI BC k minus I x to the k. So let's rewrite this as the sum k equaling 0 to A plus B of, well, this thing in the middle, all times x to the k. So this is sum I equaling 0 to k, ACI, BC, I minus k. Now, since these are equal, I can just say, well, this is equal to this, because by the properties of exponents. So if I have the same base, I can just add exponents, keep the same base and add exponents. And so this is equal to, by the binomial theorem, the sum k equaling 0 to A plus B of A plus BCK x to the k, 1 to the power A plus B minus k. But 1 to any power is 1. So this is the sum k equaling 0 to A plus B of A plus BCK x to the k. Now, if you look, these both have the sum k equaling 0 to A plus B, and they each have x k's. So what's in the parentheses must be the same. Therefore, the sum I equaling 0 to k of ACI times BCK minus I must equal A plus BCK. Well, that's nice. It sounds like an airplane going off in here. Okay, sorry. I don't know how to turn that off. Okay, so sorry about the noise. Oh, and that's just great. And so the niceties of being in a car. Oh, come on. What is it, 12 people's things going on? Okay, so probably number 11. The sum r equaling 0 to n of NCR is equal to 2 to the n. So if I look here, if I take this sum, well, 1 is 2 to the 0. 1 plus 1 is 2, 2 to the 1. 1 plus 2 plus 1, 2 squared is 4. 2 cubed, well, 4 plus 4 is 8. 2 to the 4th, 16. 5, 15, 16, yes. So if you keep adding up each of these, you just get 2 to the power of that row. Okay, so let me show that. So 2 is just equal to 1 plus 1. So by the binomial theorem, 1 plus 1 to the n is the sum r equaling 0 to n of NCR, 1 to the r, 1 to the n minus r. But 1 to any power is 1. So this is just the sum r equaling 0 to n of NCR. And that's what you wanted to show. So good. Let me go back here. So in a random arrangement of letters of the word mathematics, find the probability that all the vowels are next to each other. So let's do this. So there are 11 letters in mathematics. So I can choose the first letter to be any of those 11, the second to be, well, any of the remaining 10, the third to be any of the remaining 9. So my denominator is 11 factorial. Let's figure out the numerator. Well, there are 4 non-vowels, consonants. So I'm sorry, 7. There are 7 non-vowels here. And so you can put those in, well, the first non-vowel is 7 of them. Next one, 6. Next one, 5. And so you have 7th factorial of those. Let's look at the vowels. Well, there are 4 vowels. And so you can put the first vowel in one place, the second vowel in, well, there's 4 places, then 3, then 2, then 1. So it's 4 factorial. Now, since all the vowels are together, then they can be in the first position, second, third, fourth, fifth, sixth, seventh, 8th position, but they can't be in the 9th position, because if they were, then there are not enough vowels here. There are too many vowels to be in these last positions. So there are 8 positions that it can be in. So it's 8 times 7 times 4 factorial times 7 factorial over 11 factorial, 4 over 165. Or I can think of this in a different way. I can take all of my vowels, say these are all vowels, I know they're not. Say I can take all the 4 vowels and tie them, bundle them up, take a string and tie them around the 4 vowels. So think of them as being a vowel bundle. So they're this bundle of vowels. So first off, the denominator is going to be the same. So there are 11 factorial, there are 11 letters, and so you can put them in 11 factorial ways. So now let's look at what I bundled these. So I bundled these vowels together in one vowel bundle. And then there are the 7 non-vowels. So there are actually 8 objects here that I can move around. So that's 8 factorial. In the vowel bundle, there are 4 factorial different ways to make that bundle, because I can put any vowel in the first position, any of the 4 vowels in the first position, and the remaining 3 in the second, and then 2, and then 1. So there's a 4 factorial. And so if you multiply that out, you again get 4 over 165. So you can think of, you can do this sort of bundling together to make this vowel bundle move together, because it really acts like an entry. It acts like one object because they all